Hello, my name is Nika Aromi, and for Lab 5, I decided to do it on collisions. So the goal of this lab is to predict the change in kinetic energy and position of an elastic collision. And our findings were that the total change in kinetic energy was about 0, but it was a little less. For this experiment, I had a Red Bull can and a spray bottle and pushed them towards each other with about the same velocity. I did on a whiteboard to reduce friction and slipping. And after their collision, the spray bottle moved in the opposite direction, whereas the Red Bull largely kept going in the same direction with a reduced velocity. And here's that. Fundamental physics principles at hand were Newton's second law, conservation of momentum, energy principle, and collisions. Specifically in this system, we saw it was a perfectly elastic system of a collision since the objects did not stick together. And for fundamental physics principles, we start off with Newton's second law, which is final position equals initial position plus average velocity times change in time. And we also have conservation of momentum, which for collisions indicates that the initial momentum must be equal to the final momentum of each object in the collision. And since we saw this is an elastic collision, the change in kinetic energy should be 0. And also we have the energy principle, and in this system we have translational kinetic energy and rotational kinetic energy, but since we're looking at this from a top point of view, we're going to share as more so as a point particle and ignore the rotational kinetic energy. For our free body diagram, we have the Red Bull can moving towards the spray bottle while they're moving towards each other, and since our surroundings are nothing, the change in energy is 0, hence why change in kinetic energy should be 0. There's no potential energy at hand, so it's only kinetic energy. I tracked the two objects in Tracker to get their velocities and saw their initial time, the elapsed time, in order to put all this stuff in in Glow script. And here's the initial values of everything with the mass, change in time, position, and velocity initial for everything, as well as the initial kinetic energy of both objects. And then here's the iteration of all of it to get the kinetic energy and the position update. And for our results, the position update for some reason didn't work. I couldn't figure it out, but I did get the kinetic energy being a little bit less than 0. So with it being less than 0, we can see that there's something that we're missing in our either initial assumptions, or we didn't account for something, which largely is probably like we didn't account for rotational kinetic energy, energy loss through friction, through vibration and sound, or I didn't track the location of marker that correctly, but there are energies we do not account for. Which goes into, what does it mean that it is less than 0 if this is an elastic collision? Well, real-life collisions are a little bit more complicated than just being perfectly elastic and maximally inelastic. With the two principles we learned in class, those are the two options we largely have that makes it easier to solve problems, but in real life these collisions are a bit more complicated and require you to account for many more energies present in order to get an accurate prediction. Now, what if this was a collision between cars? Well, interestingly enough, cars have crumple zones, which means that in order to increase the time that the car is in contact with another object, these cars are meant to deform so that there's more time in that collision, meaning that the person in the car, who both the car and the individual have inertia and momentum, that the person isn't injured as much and their energy is dispersed over a longer period of time, meaning that they have less chance of getting injured. But because you have a greater impulse, less injury prone, so good cars need to deform in order to keep you safe. And that is all. Thank you.